Hey there, welcome back to Graph Theory. We're going to take a look at some of the material in section 5.2 here today. It's about Hamiltonian cycles. Um, Hamiltonian cycles come up kind of, we've been looking at Eulerian circuits, right? So ways to trace every edge exactly once in a graph or multi-graph, but we are allowed to revisit vertices. This business about Hamiltonian, it just kind of flips that around. We're interested in visiting every vertex in a graph exactly once. Okay, so we don't want to repeat any vertices. So we're not looking for trails and circuits where vertices are allowed to be repeated, but we're looking for paths and cycles, vertices that are not repeated, but we still want to achieve every one. So we want to get everywhere in a graph, never returning to the same vertex twice. Okay, so I'm going to try something a little bit different here and try to write this as we go. I hope it doesn't make the video too slow or too long, but what are my goals in the video? I'll just try to be brief here. So while I want to introduce what I mean by a Hamiltonian graph, so we know what we're talking about, I want to look at a little bit of a history problem. These things came out of a product that was kind of unsuccessfully marketed by the Irish mathematician Hamilton, who wasn't always unsuccessful. He gave us, among other things, the modern notion of complex number and how we visualize them in the complex plane. But we'll take a look at a little bit of a history problem, and it'll serve as an example of trying to find a Hamiltonian cycle. And then I want to state some necessary conditions, just discuss, so look at some necessary conditions for Hamiltonicity, whatever that means. We'll find out here in a second. Right? We have a necessary and sufficient condition for Eulerian graphs. Remember, for connected graphs anyway, it's Eulerian if and only if every vertex has even degree. So that condition, every vertex having even degree, it's a so-called necessary condition, because if you're Eulerian, necessarily your vertices all have even degree. But it's also called a sufficient condition, because if all your vertices have even degree, then you're Eulerian. So it's good enough. Unlike Eulerian graphs, there aren't any known necessary and sufficient conditions for Hamiltonian graphs. Maybe one of you guys will find the first one. There's lots of necessary conditions. We'll look at some of them today. So things that are like, if you're Hamiltonian, then the following has to be true. There's lots of sufficient conditions. Things like, if this is true, then you're guaranteed to be Hamiltonian. But it turns out that there aren't any known anyway right now, at least useful in the sense that they're algorithmically approachable, necessary and sufficient conditions. Okay, so let's define what these things are before we talk about them anymore. So let's start with a definition. Okay, so I'm going to call a graph, and by the way, we won't worry about multi-graphs here, because if you're just trying to visit every vertex once along a path or a cycle, then multiple edges and loops, they're completely vestigial. So we'll just go back to graphs, simple graphs, no multiple edges. So we're going to call a graph traceable. It's traceable if it has a spanning path, spanning a subgraph that's isomorphic to a path. Right, so what is a spanning path? Well, i.e., I have a subgraph P. The vertex set of P is the same as the vertex set of G. That's the spanning part, and P is isomorphic to a path. So if you think about what that means, it means I could start at one of the endpoints of that path, move along it, visiting every vertex because it's spanning until I get to the other end. Okay, so that's what I mean by a traceable graph. A graph is called Hamiltonian if it has a spanning cycle. Okay, so G is Hamiltonian if G has a spanning cycle. That is a spanning path whose initial and terminal vertex are the same. Okay, so that's what I mean by a Hamiltonian graph. And by the way, such a cycle is called a Hamiltonian cycle. So yeah, you're a Hamiltonian graph if you have a Hamiltonian cycle. It's a spanning cycle. Maybe we should note here that if you're Hamiltonian, then you're traceable. Right? If there's a Hamiltonian cycle, well, then in particular, there's a Hamiltonian path. That path just happens to have the same initial and terminal vertex. So if you're Hamiltonian, you're traceable. The converse is false. Right? The path Pn itself shows that that's true. The path Pn is certainly traceable. You can start at one vertex and just move at one end vertex and move over to the other, one vertex at a time. But it certainly doesn't. It's not Hamiltonian. It doesn't have a cycle at all. It's a tree. Pn's a tree. Cool. All right. So we'll call something semi-Hamiltonian if it's traceable but not Hamiltonian. So G is semi-Hamiltonian. All this is consistent with our language about Eulerian. Semi-Hamiltonian if G is traceable but not Hamiltonian. Okay, so what's an example? Pn. Pn is semi-Hamiltonian. Cool. Let's look at just a teeny bit of history of this stuff. I think people actually were studying Hamiltonian cycles and graphs before this bit of history came up, but it's kind of fun. So we'll look at some history. So I've got a couple of images I want to show you here. The image on the left I generated myself with Mathematica. The image on the right I poached from the World Wide Web doing a Google search. I should shamelessly, I haven't included my URL here. I'll try to put it in the comments or the description rather of this video so that I'm playing by the rules. But for right now, let's just kind of move on. So what's on the picture there on the left? It's called a regular dodecahedron. It's one of the 5 Platonic solids, beautiful symmetrical geometric objects. This particular Platonic solid is made up of 12 regular pentagonal faces. So you take 12 regular pentagons, and you glue them again together, 3 at a vertex, 2 along an edge, and they will form this a surface, if you like, or solid object if you want to think that it's filled with something. So it's got 12 pentagonal faces, 20 vertices, and 30 edges. The image on the right is just a planar projection of it. You can kind of look at that thing and see the pentagonal faces. You just have to look at this biggest one, that outermost one. It's sort of the edges of the outermost face. So if you count in that picture, you might be thinking I have the number wrong. I said that it's got 12 pentagonal faces, and you might only count 11 over there, but the 12th one is out here. So it's this sort of projection onto the plane of this solid object. All right, so that's the planar projection. And Hamilton in the 1800s, with a wooden model, created a game in which each one of those 20 vertices represented a city in the world. And then the object of the game was starting at a city to find a route around the world in which you visited every city exactly once. And you were not allowed to return to any city that you had previously visited. All right. So that's how Hamilton marketed this game. I believe the game was called the Around the World game. And I want to look at another screen share here. I've got it set up because there's some nice pictures, and this I can give credit to. So we can take a look at this game. It was usually made out of wood. There were planar versions of it as well as um, uh, 3D models. So I'm assuming you can see this screen. I'm at a website called thepuzzlemuseum.com. Check it out. I'm sure it's a great website. But in particular, I just want to look at this one. So here's a planar version. You can see our graph, our dodecahedron graph is there with its 20 vertices. And so you would remove these pegs as you move around the world visiting a city. And of course, you can't remove a peg twice. And the rule is that you have to move from a city to an adjacent city along an edge. So there's kind of a wooden planar version of the thing. This, I believe, is a picture of the original game that was marketed not by Hamilton himself. He sold it to some puzzle company. It was never a commercial success, but you can see this is a nice historical thing in the box here. The Traveler's Dodecahedron was the name of the game. Again, wooden pegs on this, not, of course, real dodecahedron, but this 12-sided object. So yeah, it's got some kind of interesting history to it. All right, so let's switch back to the whiteboard here, if I can get the mouse to play nice. So let's see if we're back online, and let's go ahead and try to find, if we can, a Hamiltonian cycle. Let's see if we can win the game here. So let me switch to a color and make this thing not so thick. So what we have to do is try to start at some vertex and go around until and try to find a path, rather, visiting every vertex once. So let's start up here, say, at this vertex. You can see where I'm coloring it. And then let's start making our way around. I'm just going to kind of travel. I don't claim there's a unique Hamiltonian cycle in this graph, but so I'm not interested in hitting every edge. Remember, that's the Eulerian business. I'm interested in hitting every vertex. So I've made it that far around, and now I'm going to stop because I don't want to return to the original. Then I'm done, right? I can't return to that original vertex. There's lots of other vertices that I haven't. So I think it's time that we descend down into this graph. I think we should descend down into the graph, and then we can start kind of going back around. So we're down in there, and now we can start moving around the graph. Let's see if we can go this way. And again, I want to be a little bit careful because I'm trying to always leave myself an escape route back. So I'm not going to continue. I want to leave that vertex connected to my initial one. You know, that's got to kind of be my last way there, right? This edge, I'll color it in a different color here just for a second. This has to be the final edge I traverse because I've got to end up there at that initial vertex. So I think it's time to descend in again, yeah? I'm not worried about skipping edges. So which way should we go? I think we need to go this way around this thing, kind of alternating clockwise and counterclockwise. And now, do you see it? I think we made it. We visited every vertex, and that subgraph is isomorphic to a cycle. So that we just illustrated drawing a Hamiltonian cycle in the dodecahedron graph. Which I'll just denote by G here. All right. So that's just kind of an example to illustrate the notion and give you a little glimpse into some history. I've read, and maybe you saw on this website, I don't know if it said it on the screen there, but the game was never a commercial success. It didn't really make all that much money. Lots of people speculate because it's kind of too easy, that it's not really all that hard to discover how to do this. And so nobody wants to buy a puzzle if you can solve it so quickly. Okay, so let's look at some, let me check my outline here. So we've introduced what the notion is. We've got a little bit of history. Let's look at some necessary conditions. Let's look at some necessary conditions for these things. Some necessary conditions for Hamiltonicity. I got a couple of these things. We'll just enumerate them. So one is the following. If your Hamiltonian graph then you're two connected. If Ryan or Kyle were here, he could tell us, what do I mean by two connected? I mean that your vertex connectivity kappa is at least two. Does it mean that I could disconnect you with two vertices? I don't know. I don't know. Maybe kappa of G is 10, but it's at least two. I know that I cannot disconnect you with one vertex. That is, you don't have a cut vertex. All right. So I'm going to leave this as a homework problem. This is going to be, I think it's number 15 in your text in section 5.2. If I'm wrong about that, forgive me. I need to write up the homework and get it on Canvas sometime before class tomorrow. But that one I'm going to leave to you. But that's an example of a necessary condition. I'm calling it a necessary condition because it's a statement of the form, if G is Hamiltonian, then blah, blah, blah. And now the blah, blah, blah is it's two connected. All right, so necessary conditions can be used to rule out things. Yeah, if you're trying to find out if a graph is Hamiltonian or not, if you have a necessary condition, think of the contrapositive of this statement. If G isn't two connected, then it's not Hamiltonian. So to say G isn't two connected means that it must have a cut vertex. So if you have a graph with a cut vertex, then don't look for a Hamiltonian cycle in it. That's what this condition means. Okay. Let's write another one down. It's specialized off to complete bipartite graphs, but a complete bipartite graph is Hamiltonian. Sorry, I'm right. I'm changing style. I didn't write if it is. I'm kind of moving back and forth here, being a little scatterbrained. Then n has to equal m. Remember what we would call that a complete, it's called an equitable bipartite graph. Equitable. Equitable in the sense that the two parts, the two sets that make up the bipartite, in this case, n nodes and m nodes, have to have the same size. So the only way you can have a Hamiltonian complete bipartite graph is that if it's equitable. So here's the proof, or a proof, just a sketch of it. So first of all, subgraphs of bipartite graphs are bipartite. Right? You would just take the subset of the vertices in each part. Those are your parts. And it's still going to be true that things are connected if and only if they're in different parts, because you don't add any edges when you look at a subgraph, right? I mean, you possibly lose some vertices. So that's clear. So another statement is that a cycle, remember, is bipartite if and only if it had even length. Cycles are bipartite if and only if they have even length. Yeah, you take an even cycle, then it's bipartite. An odd cycle isn't. We proved that when we were looking at bipartite graphs. Hamiltonian cycles span, right? So if you have a Hamiltonian cycle, in K and M, well, it spans K and M. Every Hamiltonian cycle spans. And so we have this bipartite cycle. We have this bipartite cycle. So it must be the case that N and M have the same number of vertices in it, because it has to have an even length. And the length of it is N plus M. Yeah. The length of this spanning cycle in KNM is the number of vertices, that's n plus m. But if n plus m is even, then n and m have to be equal to each other. Why is that true? I just confused myself. I think it's true. I'm just going to state it, and we can talk about it in class rather than stopping this video and making it again. I'm just going to state that's clear. My brain is slowing down right now, so let me just move on with it. You guys can ask me about it. This will be a way for me to see who watched this video. Okay, let's look at one more. I'm not going to give a proof of it. I botched the one proof that I was going to give, but I'm not even going to try number 3 here, but let's see. It's a little bit more of a complicated statement, but it can be kind of useful sometimes. So it has the form, if G is Hamiltonian, these are all necessary conditions. If G is Hamiltonian, then for every non-empty subset of the vertex set, I'm just going to write that mathematically like this. Every non-empty subset of the vertex set, it's true that G removing those vertex has at most number of vertices in S components. All right, so the condition is if you have a Hamiltonian cycle, then anytime I pick a subset of the vertex set except the empty set, and I pull those vertices out, the resulting graph has at most the number of vertices that I pulled out components. Okay, so that's the condition on that thing. I want to use this as so that's a corollary. So I'm not giving the proof right now. Maybe if there's time in Friday, April 10th's class, we could try to give the proof, but I'm not going to give the proof right now. But as a corollary, it can give a second proof to your homework number 15. In homework number 15, I don't want you to give this proof, but as a corollary, we can say if G is Hamiltonian, then it's two connected. If G is Hamiltonian, then it's two connected. So how do we prove that from this number 3? Well, so this condition, what do we get if we apply the condition to say a subset S with one vertex? Or maybe before we even think about that, so a Hamiltonian graph has to be connected. Let's maybe start by saying that. Any Hamiltonian graph, this is another necessary condition. I could have put it in our list, is connected. Why is that true? Well, because it has a spanning cycle, right? So you pick any two vertices in this graph, they're on the cycle because it spans. So there's a path between those vertices. So a Hamiltonian graph has to be connected. So now, if we take some subset S of the vertex set and say it has one element in it, so it looks like some single vertex V, okay, then because G is Hamiltonian and property 3 holds, the graph G minus V has at most how many components? 1. It has at most 1 component. That is, it's connected. V was any vertex. We can pull it out and the remaining graph, the resulting graph, sorry, is still connected. So V is not a cut vertex. Yeah, V is not a cut vertex. You cannot disconnect this connected graph, by removing a single vertex. So that means that the vertex connectivity of this graph is at least 2. And Kyle, I think I'm actually finally answering your question, because I don't know what the vertex connectivity is. It might be bigger, but I still want to say, therefore, G is 2 connected. Good. Okay. So there's some necessary conditions. There's more. There's even more, I think, written in your text. We are going to take a look at some sufficient conditions next time. They tend to be a little bit trickier, but the conditions that guarantee a graph to be Hamiltonian. And that'll be on the Monday video lecture. I'll see you in the Zoom meeting class tomorrow, hopefully, where you can ask me about this stuff. Okay. Thanks for listening.